Welcome to Standex Electronics Reed Relay Training Module. This module will define key terms used in reed relays and their applications. The module will also describe the structure and function of reed relays and their vast number of applications. It is important to first review some of the key terms used by engineers to describe reed relays. To start, a coil composed of many turns of fine insulated copper wire, shown above, is used to generate a magnetic field that will be strong enough to close the contacts of a reed switch. When a voltage is applied to the coil, the generated current will produce a magnetic field that will operate or close the reed switch contacts, usually positioned within the coil. Removing the voltage from the coil will open the contacts or deactivate the contacts. The heart of the reed relay is the reed switch and is composed of 2 or more nickel iron leads within a hermetically sealed glass envelope. The inner sealed ends of the leads have plated or sputtered metallization to ensure long, reliable contact life. The underlayer or base metal is nickel iron, having a sputtered layer of tungsten and an outer very hard sputtered ruthenium metal located at the ends of the leads where they contact each other when closed. Several other reed switch plating materials exist, and they are dependent on the manufacturer and application requirements. The pull-in voltage is that point where the contacts close while slowly ramping up voltage. And conversely, the dropout voltage is that point where the contacts open when slowly ramping down the voltage. This voltage for pull-in and dropout is measured directly across the coil. The resistance of the copper wire making up the coil is called the coil resistance. Hysteresis is the ratio of the dropout voltage and pull-in voltage, or the dropout voltage divided by the pull-in voltage. Switching voltage is the maximum voltage capable of being switched by the contacts. The breakdown voltage is that voltage that the contacts are capable of withstanding where no breakdown or arc over will occur. The insulation resistance is the resistance across the contacts and or the resistance between the coil and the contacts. For a reed switch is typically as high as 10 teraohms. Many reed relay applications require switching many tens of millions of operations. Testing the contacts dynamically is critical to determine any tiny flaws in the reed switch. These flaws can result in early life failures. Since this parameter is so important for long, reliable reed relay life, we will take an in-depth look at it. Long reed relay life and dynamic contact resistance go hand in hand. Understanding dynamic contact resistance is an important step to better selection of the right reed relay for the right application. The contacts shown above are in the open state. When voltage is applied to the coil, the reed contacts close. They do so with a certain momentum. That momentum of the contacts coming together make the reeds vibrate in a simple critically dampened harmonic motion. Critically damped harmonic motion is an important concept in our dynamic contact resistance testing. The frequency of the harmonic motion is determined from the spring constants and mass of the reed switch. With the closure of the contacts, there's a slight vertical motion as well as a horizontal motion. This results in a scrubbing operation on the contacts. This movement is occurring hundreds of times per second. Any non-uniformity on the contact surfaces or particles will present a different frequency pattern. If there are any slight cracks or stress to the reed switch, the frequency patterns will be altered. Since the coil surrounds the reed switch, the movement of the leads is occurring in a magnetic field. Metal moving in a magnetic field will generate a current. This generated current is what we measure and call dynamic contact resistance. To test these microscopic movements, we operate the coil at about 100 times a second. This will allow us to observe the patterns on an oscilloscope. Operating at these speeds, the mechanical dynamics are being pushed to their upper limits. The dynamic contact resistance is like an electrical microscope looking at the mechanical system. And in this way, the dynamic contact resistance will show and expose any flaws in the mechanical system. These flaws represent potential early operating failures that can be eliminated and thereby never find their way into a customer's equipment. Shown above is the pattern across the contacts shortly after the reed switch contacts close. To initiate the action, a voltage is applied to the coil shown at time 0. The area highlighted in gray represents the time after the voltage was applied until the contacts make their first closure. In this case, it takes about 0.25 milliseconds. The contact bounce is highlighted in blue. In this case, the contacts have one bounce where the contacts open completely before reclosing. Highlighted in red appears to be more bouncing, but this is actually dynamic noise. The contacts never actually open, but are wavering in the magnetic field, producing full closure. And then the pressure relaxes on the contacts, but they never open. With this relaxation, the contact resistance increases. With subsequent cycles, the contact resistance becomes less and less with each additional cycle. The contacts are wavering in the gray shaded area. As shown, this can continue for almost 2 milliseconds, but should be extinguished after this time. The blue point is where we actually measure the dynamic contact resistance. The above trace shows a good closure for the contacts of a reed relay. Monitoring this pattern for any changes in the pattern usually will indicate a problem with the contacts and will lead to an early life failure. Excessive contact wavering may indicate a stress on the reed switch glass envelope or hermetic seal. Excessive contact dynamic noise may indicate a crack in the reed switch glass envelope. Torsional forces actually put a twisting force on the glass envelope, giving rise to excessive bounce and dynamic noise. This can occur from improper reed relay assembly, stress produced from the potting material, or poor lead bending or twisting. Any net force on the reed switch capsule can shorten the life of the reed relay. Any slight crack on the glass capsule will drastically reduce life. Not testing a reed relay for DCR may result in shortened life in the customer's electronic equipment. There are many types of reed relays. The contact configuration used for a given design or application is typically described by its contact form, such as 1 form A, 1 form B, etc. Contact form A is a single pole, single throw, normally open relay. Contact form B is a single pole, single throw, normally closed relay. In this case, the contacts are initially held closed by an internal biasing magnet. A single form C relay consists of 3 reed blades: a normal open contact, a normally closed, and a common contact, also called a single pole double throw. Contact form E is a bistable contact that can exist in either the normally open or normally closed state with no coil power, and is also called a latching relay. This type relay also uses an internal biasing magnet. Reed relays can have multiples of each form, up to 4 in a single package. To fully grasp the extent of the reed relay technology, it's best to describe their characteristics. Reed relays are capable of switching into the billions of operations, unlike electromechanical relays, and more like semiconductors' long lifetimes. No technology except reed relays are capable of switching 0 voltage and current. They can also switch and hold up to 15,000 volts. Reed relays have as low as 100 tempofarads across their open contacts, allowing the customer to switch very low signals in the nanovolt and picoamp levels. Insulation resistance is greater than 10 tera ohms. No semiconductor or electromechanical relay can offer isolation anywhere near this level. This gives rise to applications only reed relays can handle. Contact resistance, typically 50 milliohms, translates into less signal loss through the relay. Very high pulsed currents, up to 25 amps, are possible through the closed contacts of a reed relay. Surprising to many, the reed relay has the ability to carry very high frequencies up to 20 gigahertz, and correspondingly switching fast digital signals in the digital world serves many new applications. Contact closure is more than 10 times faster than electromechanical relays. and at closing times under 100 microseconds, the reed relays approach semiconductor speeds. They are also capable of operating at temperature extremes from -55 Celsius to 100 degrees Celsius without any additional compensation or added circuitry. This far surpasses other switching technologies. Reed relays have also shrunk dramatically, which has increased their number of applications. Even more applications have arisen due to the large assortment of different package styles and listings for certification in UL, CSA, VDE, etc. Many of the key reed relay characteristics have given rise to applications not suitable for other technologies. We will now present some of them. A very large number of reed relays are used in automatic test equipment. Some of these are used in the following: the automotive diagnostic test systems, functional PCB testers, integrated circuit testers, memory and VLSI testers, printed circuit board testers, wafer testers, automatic test equipment, whether it's testing functional printed circuit boards or integrated circuits, require up to 20,000 switching points in one of their systems. And with line widths running in the low nanometer range for the newest integrated circuits, isolation of these switching points has become ever critical. The switching devices need to be able to handle digital signals in the 2 to 4 GHz range with 50 ohm impedance and offer very low capacitance across the contacts. Reed relays are the only switching technology that can meet all these requirements. Other automatic test equipment with reed relay usage are cable testers, discrete semiconductor testers, power component testers, and more. Furthermore, with over 20,000 switching points, the switching devices must be extremely small. It is not unusual to have up to 30 layers making up the printed circuit boards that will house these switching points that are mounted on both sides of the boards. These boards are very expensive, which drives up the cost of real estate on the boards. Some reed relay manufacturers have been able to meet this challenge by offering very small reed relays in a surface-mounted package. Reed relay technology not only is the technology of choice when in the high-speed, fast digital pulse arena, but also is excellent when working with high voltages and high pulsed currents. Cable testers, for instance, need to check wire-to-wire isolation where very high voltages are used to test and guarantee no flaws exist in multiple parallel wire configurations. They need high voltage reed relay matrices to switch the voltages in a sequential manner. And when testing high power semiconductors, high voltages and high pulsed currents are necessary to verify that semiconductors can meet their high power requirements. Here again, reed relays are the design and choice for switching these high voltages and currents. Most electronic instrumentation uses an assortment of reed relays. Here are a list of some of these instruments: data acquisition testing, electrometers, printers, medical cauterizing generators, medical test systems, multimeters, RF switching and transmitting, scanners, and multiplexers. Various instruments are used to detect and analyze very small voltages and currents. Reed relays, with their very low capacitance across the contacts, is ideally suited to handle these signals without any loss in signal strength. 97% of hospitals now use electronic scalpels. These scalpels not only cut tissue, but cauterize as well. They use up to 10 amps at frequencies up to 2 megahertz. This critical technology uses reed relays exclusively. Reed relays are used throughout the telecommunications industry. Some examples are modems, line switching, pager transmit receive switching, cellular antenna switching, and line sensing. Most of these applications require certification in UL, CSA, VDE, etc. Reed relays satisfy the requirement where many instruments need to operate flawlessly, switching the AC line over millions of operations during their instrumentation lifetimes. The transmit-receive switching circuit in cell phones and pagers switch and carry digital frequencies in the 1 to 5 gigahertz range, where reed relays are ideally suited to carry out the switching function. Reed relays are the design and choice in most security systems, where they are used in the passive infrared sensors as the main switching device and are used in the alarm call-up circuits. Many battery-operated instruments use reed relays as a safety relay in its normally closed position, where it draws zero power until called upon. Also, reed relays are used throughout the industrial and robotics applications, in many switching applications and matrices. Explosion-proof environments call for the most reliable switching devices with no exposed arcing, and again, the reed relay is a great design-in favorite. The unique hermetically sealed reed switch used in reed relays presents a technology that is the design-in favorite in many applications, where other technologies simply don't meet the requirements. The reed relay's isolation and ability to handle fast digital pulses set it aside as a unique technology. Proper reed relay dynamic testing ensures long, reliable life into the billions of operations.